So in this lesson, we're going to be talking about magnetic flux, which is a really important to understand electromagnetic induction, which is probably the part that's the trickiest for a lot of students to understand. So before we understand Lenz's law and Faraday's law and electromagnetic induction, we have to understand how do we calculate magnetic flux and what does it mean to handle magnetic flux. Flux in general is a concept that you learn in the multivariable calculus class. It has a general form, and this one we're specifically going to be talking in electromagnetic or magnetic flux. All right, so the last part of electromagnetism. So just to recap what we've talked about before, is we said like, okay, a moving charge can create a magnetic field, and a charge moving through a magnetic field can experience a force. Now we can talk about magnetic fields can actually create current as well, create moving charges. Okay, so not only can moving charges create magnetic fields, but magnetic fields, if they behave a certain way, can also create moving charges. Okay, so like it's really fascinating, kind of how everything like operates together and how weird it works, how there's symmetry. But it's reality, right? There's a lot of experimentation. All of our technology is built around a lot of these concepts, electricity. So let's talk about how this works here. The first thing we got to learn is magnetic flux and how do we calculate flux, okay? So for those of you who've done AP Physics C, you would have done electric flux. It's the same idea here, so you could probably skip this. Don't necessarily need to recap it. It's just for magnetic field flux. But if you've never heard of what flux is, in general, flux is the amount of a field that's passing through a particular area. So imagine, I always like to use an analogy here when we're doing this, I think of like your shower head, the water coming out of the shower head being like the field. Okay, and the flux is like how much, like if I have a loop, if I have like a surface here, there's like an opening, or maybe it's a loop, and often it's going to be a loop in our case, but it doesn't have to be a loop. But whatever this surface is, the flux is how much is passing through here. So if I have water coming out of this hose and it's passing into this opening, that's the flux, right, to some extent. And we'll talk about the calculations, but that's intuitively what it is. Now, it matters the direction that the water is facing and the direction that this is, because if I change the opening this way and the water is coming in this direction, then less water is going to go through this hole. So it matters which way it's facing to get the full amount of the thing. Another example are solar panels. You want to aim the solar panels directly at the sun, because you want more flux. You want more of that sunlight rays to hit that surface. If you bend it further away where the sun rays are coming this way, then you're not going to generate as much electricity in your solar panels, or you're not going to have as much water going through your opening here. So flux is about how much stuff. So it matters the area, it matters how much water is coming out, or the field strength, and it also matters which way that you're orienting your surface here, or orienting your loop. So those are the three things that kind of matter here. So the flux, which we use phi, this is the flux calculation, is the magnetic field times the area, but it's the magnetic field parallel to the area vector. So what do we mean by this? This is a little bit tricky. So A is a vector. Okay, so A is the area of the surface or loop. And the direction is perpendicular to the surface. So if I have a surface like this, like a piece of, so if I have like let's say I have my phone right here. Okay, this is a surface area here. The area vector points perpendicular away from my phone surface here. Okay, like that. The magnetic flux is a scalar value. So this is the area vector, and then we care about the magnetic field that passes through there. That's why we do this cosine of theta. You look at this cosine of theta really. I just say how much of the B is passing through it. So if the B is passing at an angle, so if the magnetic field is passing at an angle like this, then I want to decompose it and only find the component that would pass perpendicular through the surface here. I would only care about this component here, because the one parallel to the component, parallel to the surface, is not going to pass through the surface there. Okay, so magnetic flux is a scalar value, but it can be positive or negative depending on whether the B and the A vectors are in the same direction, or in their opposite direction. So remember, like if you remember our work calculation is very similar to this, how we calculated work back in AP Physics 1 or in mechanics, where we said the force is parallel. If they're in the same direction as the displacement, you do positive work, opposite directions, negative work. Similar thing for flux. If the B field and the A field are pointing parallel towards each other, then we say it's positive flux. If they're pointing opposite directions, it's negative flux, okay? It's not really that important to know the sign of the flux, but just keep in mind that there is a sign because that will matter when we're doing the induced EMF. So let's take a look at this here. Following figures, loop of wire with area A is within a uniform magnetic field B. If the surface is perpendicular to the B field, calculate the magnetic flux. Here, the flux is B times A because the B field here is passing right through the area, just like that. Just multiply the two. But if it's parallel, then the magnetic flux is going to be 0 because the B field is just passing over that surface, but not actually going through that loop. And that matters because the flux part is what's going to cause that induced current in loops of wires and things like that. Okay, so that's the general idea of flux. If you found this video helpful, come check out our school community. It's got an amazing bunch of features. It's got extra videos, corrected videos, better than the ones that I have errors on YouTube. It's got multiple choice free response questions. I hold live Q&A sessions and go through more problems and I answer students' questions, help with schoolwork, all kinds of things. If you want to check it out, look in the description below or check out the website and find us in the school community. You get a 7-day free trial to give it a shot, just to check it out, see what it's like, come join some calls, and honestly, come learn AP Physics 1 even faster with us.